Dear students, hi again, this is Hassan Kourani. In this video we are going to learn the definition of scalar product of two vectors in a plane. And after that we will do some direct examples on this definition. Well, before you see this definition, I'd like to explore with you this definition through this GeoGebra activity. Well, as you see, we have two vectors u and v with known coordinates, and we got their magnitudes or length, as you know, of these two vectors. The magnitude says that it is the square root of x component square plus y component square. And probably you are asking, what is scalar product of two vectors? Product, as you know, has the same meaning as multiplication. So we are going to learn a new operation related to vectors. Previously we saw addition of vectors, subtraction of vectors, and at the end we get vector, resultant vector. Here we have somehow a new word, scalar product. Well, let me tell you that the scalar in mathematics means a number. Scalar product means the result of multiplication will be a scalar, means a number. Okay. Probably you're asking about this scalar equals what? Is it the product or multiplication of the magnitudes of these two vectors? If we multiply the magnitude of u, which is 4 units, the magnitude of v, which is 2.8 units, if we multiply 4 times 2.8, you will get 11.2. Is it this scalar product of these two vectors is 11.2? No, it's 8. What if we change the magnitude of v and let it 1, so the magnitude of v will be radical 2, which is 1.4, approximately 1.4. And if we multiply 4 by 1.4, you'll get 5.6, which is not the scalar product. Even if you change this vector again and again, you'll get different results, which is 4 times 2.2, which is 8.8, which is not this scalar product which we need. Well, what is the exact definition? How do we get this number, this scalar, as we have said? Well, the geometric definition, as you see, we have two titles: geometric definition and analytic definition. So you can deduce that we have two definitions for scalar product. The scalar product definition, geometric definition, is u dot v is the magnitude of the first vector u multiplied by the magnitude of the second vector v multiplied by cosine alpha. Who knows what do we mean by this alpha? In fact, yes, this is the geometric angle between u and v. As you see, I have translated u over and v, and we draw them at the same origin to get the geometric angle, as we said before in previous video. So as you see, we have here an angle, geometric angle 45 degrees. If we multiply these numbers together using calculator, you will get this number, which is u dot v. Well, let's see the second definition, which is the analytic definition of these two vectors. U dot v, well, it's very simple. As you see, analytic, let me remind you that analytic in mathematics means something related to our work is related to coordinates. In geometric definition, we don't use coordinates at all. As you see, u dot v is x prime plus y prime, where x and y are the coordinates of u x prime, y prime are the coordinates of the second vector v. As you see, we can easily get directly the answer. We can use, in this case, if we know the coordinates of these two vectors, we can use the analytic definition, or if you are given the geometric angle between these two vectors, you may use also the geometric definition to get the same answer. Well, now probably you are asking about this factor, this number. How did we get this number, cosine alpha, and why it's not sine alpha? To understand this, we are going to see these details. In fact, the exact definition of scalar product of two vectors is this one. What do I mean by these expressions? Well, the magnitude of u times u dot v is the magnitude of u plus or minus magnitude of u times magnitude of ah. What is ah? If you look at this figure, you can easily notice that the h is the orthogonal projection of c on this line, and the orthogonal projection of the whole vector AC is in fact AH. Let me change the position of V to see this orthogonal projection. Look at AH. It changes with a change of position of AC. Even if we take AC to the second side, still we have the orthogonal projection of AC on this line horizontally. We get AH. Let me put it here. And even if we change also AB, again H still the orthogonal projection of C on AB, and thus the orthogonal projection of AC is AH. Well, as you know, how could we get the length of this vector AH? If we consider easily this right triangle, and you know the cosine of this angle, you know the measure of this angle and the magnitude of this vector, yes, you have to use cosine alpha, not sine alpha, since this AH is the adjacent for this angle, and we don't have the length of CH, which is the opposite of this angle. If you see this note, absolute cosine alpha is adjacent over hypotenuse, so can easily get AH, which will be cosine alpha times AC, or AC times cosine alpha. And as you know, AC is equal to V. By this way we got this definition. Never mind, these details are just to understand this definition. I need you just to memorize these two definitions, the geometric definition and the analytic definition. Okay, let's see the definition in a statement. The scalar or dot product of two vectors u and v denoted by u dot v, we read it u dot v, is the real number defined by first method u dot v. As you have seen, it's magnitude of the first vector times the magnitude of the second vector times cosine alpha, where alpha is the geometric angle between these two vectors u and v. Well, the second method is the analytic definition, which is u dot v xx prime plus y prime, and also you have to memorize this definition, where u x y and v x prime y prime are the coordinates of u and v in this orthonormal system. We must have this system of orthonormal type. This is a necessary condition to use this definition. Well, let's see, as I promised you, some direct examples on these two definitions. The magnitude, we are given the magnitude of u and the magnitude of v, 2 units, radical 3 unit, with alpha, which is the geometric angle between them, is pi over 6 radians. As you know, pi over 6 is about 30 degrees. It's equal, exactly, sorry, 30 degrees. you'll be asked about the to calculate u dot v. The solution will be directly, as you see here, we don't have the coordinates of u and v, so we cannot use the easiest definition. So we must use this geometric definition: magnitude of the first times the magnitude of the second times cosine alpha, and just manipulate these calculations to get at the end 3, which is a scalar, and we are talking about scalar product of vectors. Let's see another example. Well, as you see, we have two vectors. We have the coordinates of these two vectors. So directly you can notice that we must use the second definition, which is the analytic definition, using directly the coordinates, which is x prime plus y prime, and at the end we get the needed result. Well, let's see some particular cases in calculation of scalar product. If we consider the vector u of coordinates xy in an orthonormal system, then what about the scalar product of u dot u? The scalar product, the dot product of u and itself, directly may use the analytic definition, which is xx plus yy, that leads to x squared plus y squared, and you can easily notice that it is the square of the magnitude of u, since you know the magnitude of u is the square root of this number. Or you may calculate u dot u using geometric definition, which is the magnitude of the first, which is u, times the magnitude of the second, which is also u, times cosine 0. Why the geometric angle here is 0? You know, the geometric angle between a vector and itself, since it has the same sense, if we consider two vectors that are equal, they have the same sense, thus the geometric angle between them is 0. And as you know, cosine 0 equal 1. This leads to this result, magnitude of u squared, again as the previous one. This is just for simplicity of writing. U dot u, we may write it as vector u squared, square of the vector. This doesn't mean that u times u, it is u dot u, or the scalar product of u and itself, which is, in fact, as we have said, it's the magnitude of u squared. Similarly, if we have a vector defined by two letters a and b, and when we see ab vector square, it means exactly ab dot ab, and it is the magnitude of ab squared, or the distance ab squared. Let's see this application. Given you are given in an orthonormal system the points a, b, c, and d with these coordinates, as you see, and we are asked to calculate ab dot cd and ab squared. You can see that the vectors a, b, and cd are not given, but we are given the coordinates of the points, and we can easily find the coordinates of a, b, and cd. As you see in the solution that I have prepared before, ab equal minus 4 of coordinates minus 4 minus 2. You know, the abscissa is xb minus xa, and yb minus ya gives the ordinate. Similarly for vector cd. Then at the end, you may use the analytic definition, which is xx prime plus yy prime, that leads to this result 16, and also ab square, which is as this definition. It is in fact ab dot ab, which is x squared plus y squared, and it is x squared plus y squared, which is 16 plus 4 equal 20. This is it for today, and this is your homework. Thank you for watching. See you in the next video.